Hi, and welcome to our new session here in our chapter on regularization. So this is a brief chapter on a different technique. So this is on early stopping. So I'll explain how that works as an alternative regularization technique. It's hopefully fairly simple to understand. So I guess you might already know what it means just by considering its name. And I'll also compare it a little bit to L2 regularization. So we have already seen now multiple times that especially for complex nonlinear models, we can very easily overfit. And we can also see that during optimization. Yeah? So often after we do a certain number of iterations of loss minimization, I don't know, by gradient descent or stochastic gradient descent or something else, generalization error at some point might go up, but of course training error will, as usual, monotonically go down. Yeah? Okay, yeah, we've discussed this very often before, and now the idea is to do that in a step-by-step fashion and then stop before that happens. And that's basically it, right? So if we have an iterative optimizer like SGD, well, we can monitor that step by step, and maybe we are using very small step sizes anyway. So if we do these kind of smallish baby steps, we might hopefully be able to pretty accurately at this time point here, when that happens, when generalization error actually begins to go up again, yeah, or when we maybe not improve anymore in terms of generalization, and then we would stop. So this is the whole idea. Now, one of the major requirements for that is that we don't like do extremely super large steps. Yeah. That's my I don't know. Yeah. I think this is a little bit misleading here, because we always, of course, just go for one. The idea is, if we do super large steps, yeah, in parameter space and optimization, then we might go from here to there or something like that in a single iteration, and that's what we want to avoid. Stuff like that can actually happen if we use higher order optimization, like second order, or if we would use very large step sizes in things like gradient descent or SGD. So let's assume I'm using smaller step sizes and can monitor this quite well. Now, then early stopping is really easy. So the only thing we need an estimate of this thing here, but we already know how to estimate that, right? We use test error estimation. You can just call that the validation error, like in tuning, because what we're actually now doing is we're tuning the number of iterations of our optimizer. So we will split our training set into a new, smaller training set and into a validation set. We might do that by a 2-to-1 split. So about 2/3 go into training, about 1/3 goes into validation. And we train on the new training set. We validate the error, the performance on the validation set. Yeah, who would have guessed that? And then we stop when the validation error actually stops decreasing. When it doesn't go down enough over a couple of iterations, then we would stop there, and we would use the last parameter vector where the validation error actually did decrease. And we can, of course, also do this only with single holdout splits, so with the training and with the validation set, but we can also do cross-validation, or in general any form of resampling. Which of these is appropriate mainly depends on sample size. Okay, so if you have a larger data set, you might be able to get away with a single split. For smaller data sets, use some form of iterated resampling. Here's some easy to understand pros and cons of this technique. So let's go through strengths first. So of course, this is pretty simple method. Very often it's also quite effective. You can basically apply this to any model without any further, I don't know, adjustments or complications. I guess you need to be able to do some iterative optimization. I think that holds true for many cases of machine learning models. And like I said, the steps are not supposed to be too large. Yeah, and it's also combinable with other forms of regularization. So you can actually do early stopping together with L2 regularization. That would be possible, although I'm going to argue in a few seconds that they do very similar things. but that's always from a certain, I don't know, approximate perspective. It might actually in practice be nice to combine the two. What are the weaknesses? Well, we have to peak at the validation error. We then have less data for training, at least during the tuning of the number of iterations for optimization. At the end, when we have selected the optimal number of iterations, we might include, and we often do include, the validation set and combine it again with the smaller training set to fit again with the optimal number of iterations. But while we are tuning, we have less data available, and we also have to store temporary copies of theta, because at some point we want to go back in time when the validation error hasn't decreased enough. We can actually argue that, especially for the simple case of linear models with squared loss and with gradient descent, and if we start at the origin, then early stopping has pretty much an exact correspondence with L2 regularization. And then this inverse relationship here holds, where t-stop is the number of iterations for optimizer, and this is approximately on the order of 1 divided by the learning rate, by the step size of gradient descent, times the regularization constant lambda. So this means for a small lambda, we don't regularize too much, and this would mean we perform a large number of gradient descent iterations, and complexity of the model goes up as well. It's not regularized that much. I guess that's what we've already said here, right? And vice versa. You can also visualize that. So here on the left-hand side, or in general, these contour lines here are again our risk or loss surface. Here the position of the minimizer. And here on the left-hand side, we would now do gradient descent, initialized at the origin, and then we might go along this path here. Okay, and if we would continue indefinitely, at some point we would reach the local minimum. But if we early stop, we could stop here, and that is, at least for the scenario that I outlined on the slide before, usually the location also where the minimizer of the L2 regularization is located. Okay, here's at least one simulation to show this. So this here on this final slide, this shows the solution paths for an L2 regularized linear model, and I show that the paths, how the coefficients actually develop over the iterations of the model optimized with stochastic gradient descent when it's initialized with the theta equals 0 vector versus how the coefficients develop when I do ridge regression, and I put this 1 divided by learning rate times lambda here on the x-axis. These coefficient paths actually nicely coincide. Okay, so again, I can only do this, I can only show this correspondence this nicely if we really initialize at the origin in SGD, and if I use the L2 loss, if I use this linear model here. Also, all of this is, I don't know, not super realistic. In general, we might not exactly start at the origin, and we might use more complicated losses and more complicated models. But in general, I hope that I could still argue for the reasonableness of something like early stopping, right? So we optimize a little bit less, monitoring what happens in terms of generalization performance of the model seems to be a pretty, I don't know, intuitive idea anyway. So very often this is actually being done in practice, and like I said, it's very often it's combined also with other forms of regularization. Okay, that concludes this session here. I hope you enjoyed this. See you soon.